So at this point, we haven't really figured out what makes a process spontaneous or non-spontaneous. And to get to the bottom of that, we're going to have to introduce a concept called entropy. So thinking about where we're at so far, what we've recognized is that enthalpy alone will not allow us to predict if a process is spontaneous or not. We introduced the idea of a microstate, and a microstate is a unique way of distributing the energy of a system. What we've noticed is that as the number of possible microstates increases, in our previous example this was due to the increased volume that the gas could move in, then the energy of a system becomes what we call more spread out amongst those microstates. So I just want to point out a little bit of labeling that we're going to use, a little bit of symbolism. We're going to indicate the number of possible microstates the system has using the letter W. So the question now becomes how does any of this stuff allow us to predict if a process is spontaneous or not? So a mathematical physicist by the name of Ludwig Boltzmann, he defined the concept of entropy, and he gave it the symbol uppercase S. And he said that the entropy of a system is equal to a constant, K, which is called the Boltzmann's constant, and K is just the ideal gas constant divided by Avogadro's number, multiplied by the natural logarithm of that concept we just introduced a moment ago, the number of microstates. So what we see here is that as the number of accessible microstates that a system has increases, the entropy of our system increases. Entropy, in a manner, is a measure of the flexibility of a system, the randomness of a system, or the disorder of a system. As our system becomes more sort of chaotic, disordered, random, flexible, more sort of floppy, if you will, and the number of microstates increases, so will the entropy. So entropy is often referred to as a measure of randomness. Now that's not kind of strictly correct, because if you take this to the infinite level, for an infinite system, an infinitely disordered system is not actually particularly random at all, because there's only one way of having infinite disorder. So this is kind of an approximate concept, if you will. Now what we observe is that for any spontaneous process, the total entropy of the universe always increases. So in any spontaneous process, the change in entropy of the universe, which is equal to the change in entropy of the surroundings plus the change in entropy of the system, that is always a positive number. So what that means is the change in entropy of our surroundings is negative, then the change in entropy of our system must be positive, and it must be sufficiently positive so that when we add those two things together, overall we get a positive number. If the change in entropy of our surroundings is positive, then the change in entropy of our system can be a little bit negative, provided this offsets that negative change so that when you add the two together, you get a positive number. So what it really means is that one or both of these guys must be positive in any spontaneous process. And if one of them is negative, it can't be too negative that the change in the other one can't offset it, so that when they're added together, we get an overall positive number. So this is referred to as the second law of thermodynamics, which says that the total entropy of the universe increases in any spontaneous process. And so in practical terms, what this means is that as a spontaneous process proceeds, energy becomes more spread out. We increase the number of microstates that are available to our system, to the universe. Now, that's all well and good, but how are we going to ever figure out the entropy of a complex system? For most systems at normal temperatures, determining the number of possible microstates, that W value is basically impossible. This is a protein. It's got around about 10,000 atoms, and it's got a molar mass of about 64,000 grams per mole. It's what we call a hemoglobin molecule. It's the molecule that carries oxygen around in your blood. Now, how are we ever meant to figure out the total number of rotations, translations, and vibrations that are possible for this molecule at a particular temperature? We just can't do it. There would be millions, and it's just not going to happen. So an alternative approach to figure out, to calculate the change in entropy of a system, or the change in entropy of the surroundings, is to look at the heat that is transferred during a chemical or physical change. And this is referred to as thermodynamics. So let's just kind of review how heat moves in chemical systems. And what we know that is energy will spontaneously flow via heat transfer, which we label with the letter lowercase q, from a hotter object to a cooler object. So if we have a glass of ice water, what we know is that heat will flow out of the relatively warmer water into the relatively colder ice. When we were looking at heating and cooling curves, we observed that if you transfer sufficient heat, you can actually, change the state of your substance, not only alter its temperature. So we're going to consider isothermal processes. These are processes that occur at constant temperature. And a good example of that is a phase change. Remember when we were studying heating and cooling curves that phase changes occur at constant temperature. So the phase change we're going to look at is the melting of ice. So we're going to go from solid ice to liquid ice. So in this case, the melting is occurring in a temperature of 293 K, that's about 20 degrees Celsius. The ice, of course, when it's melting, is at the freezing point of water, or the melting point of ice, which is 0 degrees Celsius or 273 K. So what's going to happen is we're going to take an ice cube. It will be at a temperature of 273 K. We're going to place it in a room that is at 20 degrees Celsius or 293 K. And melting will occur, generating liquid water at a temperature of 0 degrees Celsius, and that liquid water will be in a room in the surroundings that are at 20 degrees Celsius. So what you're seeing here is that heat is going to be transferred from the surroundings, the warm room, into the system, which is our ice. Now, you can see here that the temperature of the surroundings doesn't change, right? Because we are treating the surroundings as an infinite source of heat. That is, the temperature of the surroundings doesn't change, and neither does the temperature of our system. Now, we can get away with treating the surroundings as an infinite source of heat in this case, because the surroundings are like everything in the universe other than our tiny little ice cube. So it makes sense that we're really not going to change the temperature of all of that matter in this process. Okay, so we know that to melt 1 mole of water requires 6.02 by 10 to the 3 joules of heat. So that heat is going to get transferred from the surroundings. So in this process of going from ice to liquid water, the system will gain 6.02 by 10 to the 3 joules of heat, and the surroundings will lose 6.02 by 10 to the 3 joules of heat. Now, mathematically, it can be shown that the entropy change accompanying an isothermal process is given by the heat transferred divided by the temperature in Kelvin. So Q is just the heat transfer. So we can go ahead and do this for our system and surroundings. So for our system, the entropy change will be the heat transferred, 6.02 by 10 to the 3 joules, divided by the temperature of the system, which was 0 degrees Celsius or 273 K. And so when we do that, we see that the entropy of the system has increased by 22.01 joules per degree Kelvin, or per Kelvin unit, we should say. The entropy change of the surroundings is going to be equal to the heat transferred from the surroundings, which in this case is minus 6.02 by 10 to the 3 joules, divided by the temperature of the surroundings, which in this case was 20 degrees Celsius or 293 Kelvin. So the surroundings decreases its entropy by 20.51 joules per degree Kelvin. So in order to predict spontaneity, I have to calculate the entropy change of the universe and see if that number is bigger than 0. So I have to add together the entropy change of the system with the entropy change of the surroundings. And when I do that, you'll see in this case, I get a positive number. So the fact that I got a positive number for the change in entropy of the universe tells me that this process is spontaneous. So after a bunch of algebra, I figured out something that hopefully is obvious to all of you, that the melting of ice is spontaneous if you heat the ice above 0 degrees Celsius, which is hardly a surprise, right? But, you know, it's kind of nice to have a little kind of confirmation that our math is working. Okay, so it makes sense that the melting of ice is results in an increase in entropy of the system, because in solid ice, the translation, rotation, and vibration of the water molecules is severely limited because the ice molecules are locked into a crystal. Whereas in liquid water, there's a lot more freedom of the molecules. They can move around a lot more easily because they're not locked into this crystalline structure. And so, yeah, it just kind of, the particles just have more kinetic energy and they're able to move more. So we would expect that delta S system here is going to be greater than 0. Similarly, it makes sense that our surroundings reduce their entropy because we took a bunch of heat out of them, and that makes everything cool down in the surroundings. So, you know, overall, this is kind of very logical. Okay, so let's do the same thing, but this time we're going to do a higher temperature. What about if we take our ice cube and we don't put it in a room that's at 20 degrees Celsius, we put it in a room that's at 100 degrees Celsius? So are we going to expect it to be more spontaneous, less spontaneous? What do you think? Let's see what happens. So we're going to go ahead and calculate the change in entropy of our system. The amount of heat required to melt the ice has not changed, so our system will be gaining 6.02 by 10 to the 3 joules. And the temperature of our system is still 273 K. So the change in entropy of our system is exactly the same as what it was before. Now for our surroundings, again, the heat lost by our surroundings hasn't changed because the amount of heat required to melt ice is a constant. But the temperature of our surroundings is bigger. Now it is 273, whereas previously it was 293. Okay, so that means that we're going to have a different change in entropy of our surroundings. To get the change in entropy of the universe, we have to add together the change in entropy of the system with the change of entropy of the surroundings. And when we do that, we got a value here of 5.9 joules per Kelvin. So again, that's a positive number. If you put an ice cube in a room at 100 degrees Celsius, you guessed it, it melts, right? So, you know, ice melts when you heat it above 0 degrees Celsius. So this is all kind of like, you know, consistent. So is it more or less spontaneous than what we saw previously? Well, when we did this at 20 degrees Celsius, the entropy change was about a quarter of what we see at 100 degrees Celsius. So that's kind of logical, right? You know, there's going to be a bigger difference in temperature there, and the process, we're getting a bigger negative, a bigger positive change in entropy of the universe. Okay, so I'd like it if you'd have an attempt at these 4 problems here, and I'll be available to go through these problems with you on Wednesday during the Zoom session.